Today we will do the simulation of Maxwell Fish-Eye and Half-Maxwell Fish-Eye based on graded photonics crystal. So the fundamental of this paper is based on the spatially dependent materials. And what is the property of spatially dependent materials? That their electromagnetic properties are changed with distance. So here in this paper, there is a Maxwell's fish-eye and Half-Maxwell's fish-eye. Here in this paper, our material is spatially dependent. So we will use this formula for spatially dependent material, that is nr equal to 2 upon 1 plus r upon capital R whole square. Here value of small r is under root x square plus y square plus z square, and the value of capital R is 0.5. So let's do this in HFSS here, and its radius is 450 mm. If after giving the dimension, if you are not supposed to see your figure, then just do Control D. After pressing Control D, you will get your geometry. Now we will draw a cylinder in YZ plane. So just change here from XY to YZ. And the dimension of the cylinder will set as 800, 0, 0. The radius of the cylinder is 500 and the height is minus 1400. So here you can see that this cylinder encloses the sphere. Now we will assign the spatial property to this sphere. So we are here considering a material with spatial property. So we have to create the material in HFSS. In HFSS, select the cylinder, double click, and in material we will click on edit. Then we will add a material. Now for this material, we are having the formula, that is 2 upon 1 plus, then in a bracket under root x square plus y square plus z square upon 0.5 and the whole square of this term, and then square of whole term. Okay, so this formula was written in Notepad. So just write this formula in Notepad and select it and copy it. Then paste this formula in permittivity value. So in permittivity value, I am pasting the formula. Then OK, and assign material 1 to sphere 1. Apply OK. Now sphere 1 is spatially dependent material, and now we will apply the boundary to the cylinder. So select cylinder 1, right click, assign hybrid FEBI, that is finite element boundary integration. This boundary is applied for the infinite open region. So we choose this boundary, then OK. You can see in hybrid region FEBI boundary is created. Now we will apply the excitation. So for applying the excitation, we will just go on HFSS, excitation, assign, and then in incident wave we have Gaussian beam. So just select the Gaussian beam. Now we will provide the coordinate to Gaussian beam. So on x coordinate we will provide it -1000, and for y and z it will be 0. Then the direction of the electric vector will be in z direction, so it becomes 0, 0 and 1, and the direction of wave propagation will be in x direction, so it will be 1, 0, 0. So now here you can see that from this direction the wave will enter in this region, and the size of the beam we can take it as 300 millimeter. Now in setup, select advanced, solution frequency is 1 gigahertz, OK, and just validation, and then analyze all. So I am creating this as project 11. Now it will take some time for execution, and for more clear visualization click on this, then go on plot, outlines, and you can see the result. I am just deleting this, and I am not deleting the excitation and analysis. In the same environment, I will design Half-Maxwell Fish-Eye. So for this, again, create a sphere and just provide the radius 500 mm. Apply OK. And then we will split the sphere in half. So just select the sphere and then split. We will split it in YZ plane in positive side. So after doing this, you can see the sphere will looks like this. Now we will select the XZ plane. So in XZ plane, I am creating a rectangle. So just create a rectangle and now provide the dimension. The starting point from 800, and for Z it is 300. The dimension of X is -1100, and in Z it is -300. So these are the dimension. Now select the swap around axis. So here you can see this symbol is for swap around axis. So when you will place the cursor here, you will find swap around axis. Just click it. We will swapping it around the x-axis. Okay, so it will roll up like okay. So when we will do the swapping, we will find this kind of curve. Okay, so now this sphere is, this is the boundary of the sphere, and this is the cylinder passing through the sphere. Now do one thing, select rectangle 1, just copy and paste it. So we have two similar cylinders, rectangle 1 and rectangle 2, and there is a sphere 1. So now select rectangle 2 and sphere 1 and intersect them. So this will be the sequence. First you will select the rectangle 2, then sphere 1, and then intersect. So here you will find that this lens will insert in this cylinder. Okay. So for rectangle 1, it will be vacuum. And rectangle 2 is the spatially dependent material. So for rectangle 2, this is spatially dependent material, and we will assign it material 1. We have already inserted the formula. Now we will assign the boundary to rectangle 1. So in a similar way, we will do right click, assign hybrid, FEBI. So this is finite element boundary integration. We have already assigned the incident wave, and we have already do the setup. So now just check the validation and analyze all. After completing the simulation, we have already set this electric field. So here you can see that for Half-Maxwell Fish-Eye, what kind of diagram you will find. If you want to see more precisely, then select them and cross them. So here this is the simulation of Half-Maxwell Fish-Eye, and previously we have seen the full Maxwell Fish-Eye. Finally, in this lecture, you will learn two new things. First is finite element boundary integration, that is hybrid finite element boundary, how to apply this. Second, how to apply the Gaussian beam as an incident wave. And third, how to analyze the spatial dependent materials. Thank you.